So I'm going to give you an introduction to linked data. It's an approach that is being used by pretty much all organizations, individuals who are attempting to create fair infrastructures. So linked data is based on a technology called Resource Description Framework. And when we say it's a framework, it's because it's a way of conceptualizing how to represent data and knowledge. There's a variety of ways to implement it, and so it's not a language per se, and it's not a file format or a syntax, although there are syntaxes for RDF. It's mostly a conceptualization of how to represent data and knowledge. And the conceptualization is that all data and all knowledge can be represented through a combination of very simple statements that are called triples. And so very much like a human language, the statements take the form of a subject and a predicate and an object. And you put many of those small statements together, and in principle, there seems to be some proofs for this, that it can express anything. So because I have a wide range of different audiences, not only from the medical studies, but from many different domains, I use my cat as the demonstrative topic for an introduction to RDF. So this is my cat, and he's lovely. And so here is how I describe my cat as triples. So Mark, me, owns, that's the predicate of the statement, and cat is the object of the statement. And then the cat subject has a name, predicate, and the name is Stormy. And then we glue these two triples together. So Mark owns cat, cat named Stormy, and we make the object of the first triple the subject of the second triple. And then we keep going. So Mark owns cat, cat name is Stormy, cat's breed is British Long, Mark's residence is Madrid, and Madrid has a population of about 6.2 million if you look at all the communities around it. And this is often visualized, and you'll see in the next hour a lot of pictures like this. These are visualized as what are called graphs, and graphs are a set of nodes and connections, all of them labeled, that describe the structure of this resource description framework model. So you can see on the, let me just switch on my pointer. So this is the Mark owns cat, and cat's name is Stormy. What's interesting about these connections is that I haven't indicated, but they are directional. So it's not that the cat owns Mark, it's that Mark owns the cat. And in fact, the relationships are directional. So this is a directed graph. And what we call these different components resources and literals and predicates. So the blue things are the resources, the predicates are the green things, the connections, and then the literals are where the actual data is. So literally the word Stormy, and literally the word British Long, and literally the number 6.2 million. And the rules of RDF are really quite straightforward. There's nothing smaller than a triple, and only resources can be subjects. So on the left-hand side, I say cat, his name is Stormy, cat has breed British Long. On the right, I say cat has a name Stormy, which has a breed British Long. The one on the right is illegal because on the right, I have Stormy as the subject of the breed British Long triple, and a literal cannot be a subject. So you only can have subjects as resources as subjects. And that's pretty much all the rules there are. You've just learned everything you need to know about RDF. The way that we use RDF on the web is as follows. So resources are assigned URLs, and predicates are assigned URLs. And then literals are just literally either strings or words or sentences or dates or numbers, things like that. So the fairified, the webified version of my cat is that my cat has a unique identifier, which is this URL. And then the predicate I pick from a popular vocabulary called FOAF, which is friend of a friend, and they have the name property. And then I invented this one, but I could probably look up something similar. So I invented one called hasbreed and made it into a URL. Normally you wouldn't invent, but this is just for demonstrative purposes. So this is what my cat looks like in its RDF representation on the web. This, I want to just note, is not a web page. This is my cat. So this is like a digital twin of my cat in the real world. Right, so you don't think about RDF as web pages, you think about RDF as the unique identifiers of things in the real world so that we can talk about those things in the real world on the web. So what are the benefits of doing this? I'll talk to you about some of them, but not all of them because we don't have a lot of time. So first of all, these URLs are globally unique and shared because they're on the web, so anyone can use this URL, right? Not just me, anyone can use that URL. And in fact, anybody who knows the identifier for my cat can also use this URL, and they can then make statements about my cat. Right? So they're globally unique, they're shared, and they're unambiguous. Right? And again, don't think of them as locations. They're not web pages. They're not places on the web. They are actually the names of concepts and things in the real world. And they can be automatically looked up. So I can, in fact, call over the web this address, and that will generally return to my machine information about my cat. But the big benefit of RDF is that it makes it very, very easy to integrate data from one site to another site. So here's my graph, which is my cat has the name Stormy and my cat has a breed British Long. The pet shop where I got my cat might have their graph, which is, my cat has parent. This is the identifier for another cat, which is the parent of my cat, and his name was Snuggles. So if I want to integrate the data, what I do is I merge on the nodes that are identical, right? So these identifiers are globally unique, and they are globally unique identifiers for the thing in the real world, my cat. So I can unambiguously and completely safely merge the two graphs with the knowledge that this and this absolutely must refer to the same thing. So I flip that node down, I flip the predicate, and I join here. So now I have cat named Stormy, cat breed British Long, cat has parent, pet registry LA099, which has a name Snuggles. And machines can do this completely automatically. So I keep talking about how RDF, the nodes in RDF and these URLs are not web pages. So what is the relationship between RDF and the web? And this gets into another reason why we want to build this fair infrastructure, this global fair infrastructure, because it's extremely difficult to do data integration on the web. And I'll show you exactly why right now. So here's a web page from Orisabase, which is a database of rice genes. And they're talking about the gene AGR1, which is to do with sensing gravity. And down here they have a section called Gene Ontology, and I'm sure a lot of you are familiar with the Gene Ontology. And they have a label called Multicellular Organismal Development, followed by a colored GO007275. We know from our experience using the web that when something's colored, it's usually clickable. So if I click it, I go to this page, which explains, in fact, this is a different link right now, but imagine they were the same link, that explains a little bit more about that, that annotation. So I want you to do a thought experiment. So here's a link, and please feel free to speak and switch on your microphones and talk for a second. What happens, so this is not the same link, this is the next one. What happens when I click that link? It's not a trick question. Well, it is a trick question, but the answer will be obvious, so you can speak up and tell me.
You see some content.
You'll see some content, yeah. What content?
That depends on the link itself, right?
Yeah, but that's that. I mean, tell me what content you think you're going to see.
I probably accept like an HTML page to be shown because it's a link.
Yeah. I mean, everything about what you expect is based on your eyes looking at that web page and seeing a section called Gene Ontology and a label that says multi-structure, multi-organismal development, followed by a link. And your intuition says, if I click that link, I'm going to go to a page that tells me about multicellular organism development. But in fact, the real answer is you have absolutely no idea where you're going to go when you click that link. Right? You could go to a video about multicellular organism development. You could go to a Wikipedia entry. You could go to, in this case, the Gene Ontology entry. You could go to a PDF document. You don't know. And in fact, you don't know even that you're going to go to any site that has anything at all to do with multicellular organism development. The only reason you click on that link is because you trust the person who published that page. And because of this web of trust, the web works really, really well, because for the most part, until we get into the spammy part of the web, for the most part, we can trust the publishers, and they do send us over links to other pieces of information that we really like. The problem is that machines can't do this. Machines don't intuit, and machines don't see the web page either. So they don't make the association between the column on the left that says Gene Ontology and the link on the right. Right? We're visually making that association. Machines can't do that. Right? So humans know what the link means. Right? They think they know what the link means. It means that rice is involved in gravitrophism. But there's about 1.3 trillion gigabytes of data on the web. We can't explore all of that as humans. So we need a web that can be explored by machines. And so we need to make this information explicit. So what you do is you say, okay, this page is about AGR1, which is a gene, and it's in the taxon 013681, which is rice. And AGR1 positively regulates gravitrophism. This page is about gravitrophism, and it's a biological process that affects trait 043, which is root anatomy. So now all of the information from this page over that link to this page is now explicit. And in fact, this is the new piece of information. Right? This page did not say that the regulatory relationship was a positive regulation. It just said this is an annotation of that gene. So we're making this as explicit as we can, putting as much information as we possibly can to connect the different concepts of AGR1, which is a gene, and gravitrophism, which is a process. And in principle, I don't work in the web at all. I work only in the RDF world, just because I I design technologies to do that. So in my perfect world, we just eliminate the web and we dynamically build web pages for human visualization based on this explicit information. There are ways of embedding RDF into the web language HTML. So the two technologies are not mutually exclusive, but I'm not going to teach how to do that. So this is called the semantic web. The reason it's called the semantic web, the semantic web is one step above linked data. So linked data is these graphs. It becomes a semantic web when you add these nodes. So type gene and type biological process. If you don't add those nodes, the machine will never understand what this is and what this is, because they're just web addresses. So what you do is you ground them into ontologies. So the gene ontology and the sequence ontology both have the concepts of a gene. And so you ground this node and say, this is of type, and then you point to the concept definition. And similarly here, gravitrophism, you point to the concept definition of a biological process. And so now the machine knows that genes regulate processes. It wouldn't have known that otherwise, and that's where the semantics of the semantic web come from. And so if we want to get a sense of how much information is available, as it's called linked open data, there's 1,255 data sets that have been recorded by this project called LOD Cloud, a minimum of 1,000 triples each. Somewhere in here is UniProt, the protein database, which contains 84 billion triples. And again, just for context, all of this purple is life sciences. The black lines are the interconnections between databases. So when I create a triple that points outwards to another database, they will create a black line. And you can see that in the life sciences, it is black. The interconnections between our databases are extraordinarily rich. And so one of the biggest fair communities is the life sciences, because we've already invested so much money and effort and careful time into building these linked networks. Okay, so do you want to take questions between the talks, or should I just go straight through?
Maybe just straight through, and we can have the questions at the end.
Okay, that's fine. Okay, so Rajaram is up next. Rajaram, I'll switch slides when you tell me.
Yeah, that's fine with me, Mark.
Perfect.
So yeah, you can put it in presentation mode when you're ready.
I'm doing it. Yeah, I'm just waiting for it to reload. Okay.
Yeah, thank you, Mark. So yeah, let's we made like a semantic model, like common data element, right? Like the presentation is about that. So these are like a list of common data elements that JRC people might have seen it. So this is like a first few elements from a common data element. Can you go to the next slide, please, Mark? And yeah, rest of the common data elements, like JRC people did really good job like identifying like this common data elements, and even like some cases like assigning like a primitive types to them, right? So this is not enough. Why? Next slide, please, Mark. So the common data element proposed by JRC people like improves interoperability for some elements, like take like a patient pseudonym ID. They say like for this particular element, they even like recommend like what kind of primitive type should be used for the missions, right? Like they say it's a string. But if you take like other elements like sex as birth, like you see like list of like a possible like genders that can be assigned as a value for this element. This might be like interoperable for human, but you can imagine like the implementation might the implementers like might provide like different variety of these options. So, and for sure, like this is not like a machine interoperable at all. So what's our solution is like to improve the interoperability for this kind of CDEs is like to implement like RDF-based models to represent them. That's what we did. Next slide. So what we did was like we created like 10 smaller like semantic models to represent CDEs, which is available in GitHub page in EJP RD organization. And in our GitHub page, this is what we have, right? Like we have like an example of RDF for CDE, or like all of those several smaller models. And for human consumption, we have like a visualization of that RDF. So once you make that RDF, you have to evaluate, right? Like if that RDF like go in sync with a model. So for that, we have like the shape expression, which is like a validation artifact that validates your RDF. Next slide, please, Mark. So this is like our first version of CDE model. As you can see, it's quite elaborate. It's large. So this version of model is like semantically rich. It's very rich, but it took like quite a lot of time for us to come up with this model. And you can also see here, like we used different patterns for each CDEs to represent using this model. So for people who are new to semantic web technology, they might find it hard to like query this model if they want to use it. So next slide, please, Mark. So then we started asking, like, is there like a generic pattern to represent all those different CDE cases? And that's when like Mark joined us and he proposed some solutions, which he can walk us through now.
Okay, thank you. So as Rajaram said, the complexity of this model is problematic for two reasons. One is that every different CDE has a different structure, and that makes it difficult for the people who have to fill the models, because they will have to memorize or learn or code to each of these structures independently. But the second problem is not just filling the models, but querying the models. One of the objectives of the EJP is to have a query builder, so that it will either automatically or guide the user through the construction of a query. If every kind of data has a different structure, it's extremely difficult to build an automated query guidance system, so to speak. It would be so much better if every piece of data was represented in basically the same way. So we went through the CDEs, and I have some background in a particular ontology called the Semantic Science Integrated Ontology. The leader of that project is Dr. Michel de Montier, who's at University of Maastricht. But I've been working with the SIO for a long time. I'm co-author on the paper, and I've been working together with Michel during the development of these CDE models, because we needed him to tweak and twiddle some things in the SIO itself in order to better represent our scenario. So let me take you through the core model for all CDE data, and then we'll look at one fully fleshed out one. So the idea here is that there's an identifier that denotes a particular role, and a particular entity has that role. So for example, my driver's license ID denotes my role as a driver. My hospital ID denotes my role as a patient. My passport ID denotes my role as a citizen, and so on. Right? So there are different kinds of entities that have different kinds of roles, and each of those roles is associated with some identifier. The role of a patient is realized in some kind of medical process. The role of a driver is realized in the process of driving. So I have a role which is realized in a particular process, for example, blood pressure measurements, genotyping, questionnaire answering, a registration, donation. These are all kinds of processes, and those processes have a particular output or an observation or a measurement. Entities have qualities. So quality of systolic blood pressure, quality of date of birth, date of death, various other kinds of qualities. And those qualities are the basis of these observations. So that's the entire model. Identifiers denote roles, entities participate in those roles, entities have qualities, there's a process to measure that quality. So let's look at what the CDEs look like when you put them into that model. Now, don't get scared. I'm going to walk you through this very, very carefully. Right. So this is a linked data graph. At the top, we have a person. And that person has a quality, and we're going to call it quality 1. Quality 1 is of type birth date from the Open Biomedical Ontology's Ontology. I can't remember which ontology exactly it is, but it's an ontological concept. And remember that the way that we get semantics in graphs is by putting a type on every node. So this is a birth date quality. A person has a role, call it role 1, and that role is as a patient. So it's RDF type, patient. Again, patient is coming from, patient role is coming from a specific ontology. That role is realized in a process. The process has an output, call it output 1. And output 1 is based on the quality of birth date. So you'll see that this quality is the basis for this output. And the output has a value of the date of birth. There's another quality called gender, so quality 2 called gender, which is the basis for this output here, output 2, which is of type, and this is the SNOMED code, again, in ontology, for feminine gender. There's some other nodes here that are mainly used by us for generic kinds of queries. If we want to just query any process, any quality, any output, we can generify our queries. So again, identifiers denote roles, entities have roles, entities have qualities, roles are realized in processes, and qualities are the basis for the output of those processes. And so rather than, if I zoom back, rather than just saying patient's date of birth is this date and patient's sex at birth is one of these words, we now have a much richer model where we can put additional information. So the quality of birth date, whereas here, the quality of birth date is just a date. Here, it is a thing in the real world which could have additional annotations. So that quality was measured by some process. Who was involved in that process? Who measured the birth date? Who took the survey? Who determined the gender? On what date? Right? This process can now be annotated in a much richer way than simply these very, very basic fields. And so we've gained a lot of additional power, which we don't have to use. Right? We can just say there is a process. We don't have to annotate it anything beyond it has an output. But if we know more about it, there's a very clear, unambiguous place in our model to put that information. When did the process start? When did the process stop? Who was the physician? How was it recorded? What machine? What version of software? Right? All of those things have a place in the model if we ever want to add them. So we immediately are able to take CDEs and extend them into much, much richer data representations. And again, unambiguously, we know exactly where those annotations go. Okay, so that's the end, I think, of that presentation. So now we'll move on to the last one, which is about how are we going to get the data from registries into these models? Because even though we've simplified the model, it's still not trivial to do this. Right? So let me show you how, at the moment, how we think we're going to do it. So again, I'll go into preview mode. Okay, so how are we going to fill these models with your data? So the way that we're approaching it right now, this may change because we're still in the early days, but I think we're on the right path. So we're going to use comma-separated value files as the lingua franca between you and registry owners and biobank owners and us, the verifiers. So CSV is a simple format, fairly universal, easy to generate from the most common data collection systems. So spreadsheets can output CSV, databases can output CSV. So it's a fairly universal and straightforward format to generate from the perspective of the person who owns the data. We will then, so we are going to create template CSV. So we're going to tell you the first column must have this kind of information with this header. Second column must have this information with this header. We're going to have standardized column headers showing you what data you need to provide for each of these CDEs. We will then pass that CSV through a transformation pipeline using this emergent set of technologies called YARML and RML. Let me just talk to you a little bit about these technologies. You'll see just how contemporary these technologies are. So the unofficial draft of RML was published on July 2020, written by Dr. Dimou at Ghent University. It's an extension of this pre-existing language called R2RML, and it handles input from databases, CSV, TSV, XML, and JSON. I've been using it again for a few iterations, so it was first generated 2 or 3 years ago. It's much more mature now, but I've been using it for a while because it seemed to solve a lot of problems. So what it looks like is this. So here's our input. So for example, you have an ID number of this. I don't know, stop number of this. I don't know what these are. I guess these are airport codes. Latitude is this number and longitude is this number. This is what an RML mapping file looks like. It's not a trivial document to interpret, but basically it says we're going to create a subject and the template for the subject is this, and at this point in the model, we're going to grab the value from the ID column. And again, here, the reference for this node, which is the predicate, is going to be stop 25 and things like that. All right, and then you apply the mapping to the input and it generates triples. So example.com 6523 is of type stop. And 6523 has a transit route 25. And so these are the triples that come out after the mapping. Now, these are nightmarish. They're nightmarish to maintain, they're nightmarish to write, they're nightmarish to modify, and they're hard to read. Right? So another couple of researchers from Ghent have created a easier human readable language called YARML, which creates declarative rules that can be used to automatically write these files. So it's a technology for writing RML files, which is the technology for transforming CSV files. So this is a much easier, say, serialization to read than RML. And you can also add some interesting conditionals. So for example, if this, then do this transformation. If something else, then do some other transformation. So this is still immature, but they're planning to make it a standard part. And again, this is all very, very recent.